S. Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
What are the wave equation, heat equation, Laplace equation? All of us must have come across these terminologies, wave equation, heat equation. So, and then we have come across with these terminologies also hyperbolic equation, parabolic equation, elliptic equations. So, we are going to discuss these things today.
If you want to study this topic in detail, refer to the book by S. Chan Publishing. Link is provided in the description box.
So, welcome to S. Chand Academy. I, Dr. Neelam, will be discussing this classification of the second order partial differential equation today, where we will discuss these things in more detail. So, we will be considering the classification of differential equation, partial differential equation. So, for that, particularly we will be classifying the linear second order partial differential equation. So, first of all, we will see that linear second order partial differential equation. So, if we and we have already made it clear that this partial differential equation abbreviation is being used for partial differential equations. So, here our independent variables are, let us say, x and y, and the unknown function is u. So, if it is a linear second order partial differential equation, then it will involve the second order derivative of this unknown function with respect to these two independent variables. Now, it is not necessary that there can be only two independent variables, but we are taking for two independent variables for this case. So, that means the equation which involves del u over del x, which can be written as ux with x in the subscript, then del u over del y, where y will be written in the subscript, and then it will involve three second order derivative, del square u over del x square, which will be written as uxx, del square u over del x del y, which will be written as uxy, and then third derivative of second order will be del square u over del y square, which will be written as uyy. So, these two will be the first order partial derivatives, and these three will be the second order partial derivatives. So, any equation which involves at least one of them, it is not necessary that one equation should involve all three second order partial derivatives, then only it will be called as second order partial differential equation. Even if it involves any one of them, it will be called as second order linear partial differential equation. So, we will see that, let us say that A uxx plus b uxy plus c uyy, and then since it may involve the first order partial derivative also, so dux plus euy plus fu is equals to g, where the coefficients a, b, c, d, e, f, they are the coefficients of the unknown function and its derivative and the free term g. And this free term g are the functions of, they may be functions of the independent variables. So, since we have taken independent variable as x and y in this, so they may be functions of x and y, but they needs to be free from u and its derivative. We have to be very sure that they should be free from the unknown function and its derivative and its derivatives. So, this is the general form of the second order linear partial differential equation. And it is clear that this A, B, C, D, E, F, they are they may be functions of x and y, and they may be constant, and this similar condition is applicable on this G, which is the free term on the right hand side, which does not involve any u or its derivative, where u is the unknown function. Now, we need to find out the classification of such a differential equation. So, we will be studying the classification of second order linear partial differential equation. So, we are going to use this terminology only. Whenever we are following any particular method, so we need to be very particular about the terminologies. So, we are taking this AUXX plus BUXY plus CUYY plus DUX plus EUY plus FU is equals to G. Now, since we are doing the classification of second order linear partial differential equation, therefore, the leading terms, these three terms are there which involves the second order derivative. They will be playing the leading role, and the rest of the terms, they can be taken to the right hand side. So, this partial differential equation can be rewritten in this form: AUXX plus BUXY plus CUYY, and rest of the terms can be taken to the right hand side, and they can be written as function of u, ux, uy, or x and y, because g can be function of xy. So, rest of all the terms we have taken to the right hand side. So, these terms will be involved in classification of the partial differential equation, which is of second order. Now, so for the classification of this, we will find out the discriminant for this. So, the discriminant for this is, discriminant will be written as b square minus 4ac. So, this can be represented as delta. Now, since this b, a and c, they can be either constants or they may be functions of x and y. So, it is not necessary that this discriminant is going to be constant, but this discriminant can be the function of x and y. Now, depending on the sign of this discriminant, we will be classifying the second order partial differential equation into three categories, because these three conditions are possible for this. So, classification at some point x naught y naught. Classification of the second order linear partial differential equation at some point x naught y naught. So, at this point x naught y naught, we will find out the sign of this derivative, the discriminant. So, there can be three possibilities. So, either the discriminant can be positive, or the discriminant can be equal to 0, or the discriminant can be negative. We cannot think of any other possibility, because now the value of the discriminant will be constant, because this point will be a constant point. So, this xy will be replaced by x naught y naught. Therefore, the value of this discriminant will be constant, and either it will be less than 0, greater than 0, or equal to 0. Only these three possibilities are there. So, if it is greater than 0, then this type of if this discriminant is greater than 0, this will be called as hyperbolic. That is, the given differential equation will be called as the hyperbolic partial differential equation. If it is equal to 0, it will be called as the parabolic partial differential equation, and if it is less than 0, it will be called as elliptic partial differential equation. So, this is the classification of second order linear partial differential equation. Now, in some of the books, instead of this form, another form is being used where we do not use this 4 here. Now, let me tell you the reason behind that. So, if we are taking this, we can say the second form of the second order linear partial differential equation. So, if it is written as auxx plus 2buxy plus cuyy, and then rest of the terms which involves the unknown function, its first order derivative, and the unknown variables, the independent variables, unknown function, and the first order derivative of the unknown function. If it is written like this, then it can be written in the matrix form. So, the constants can be written in the matrix form. So, it is A, C, and here B is written. So, if this is the form of our partial differential equation, then this matrix form can be written for this. Then we will find out the determinant of this. So, let me say that this matrix is represented by M. Then we will find out the determinant of M. So, if we find out the determinant of M, this is AC minus B square. Therefore, we must be very, very careful which form we are using. So, if we are using this 2B here, then it will be for AC only here, and if we are using B only there, then we are going to use this B square minus 4AC kind of terms. So, if we would like to classify in case of this determinant, then at some point, similar type of classification, at some point x naught, y naught. Well, again there will be 3 possibilities. So, if it is determinant of M at x naught, y naught, either it will be greater than 0, or it will be equal to 0, or it will be less than equal to 0. So, this side is determinant of this matrix form M at x naught, y naught. So, if it is greater than 0, so if we can recall from the previous form B square minus 4AC, so it will be opposite to that. So, when it is equal to 0, it is for sure parabolic. And if it is greater than 0, then it is elliptic. And if it is less than 0, then it is hyperbolic. So, we have to be very, very careful while writing down this formula, and then correspondingly we are trying to find out the classification of the given differential equation. So, we will take some examples to make it more clear that how to classify these differential equations. So, we are going to use these 2 examples to make the method more clear. So, we need to classify these 2 differential equations which are second order partial differential equations. So, we will be doing it in both the ways. The first way is that we will be finding out the discriminant B square minus 4AC, which is delta, and second method is AC minus B square, that is the determinant of this M. Okay. So, for this we need to compare it with the auxx plus buxy plus cuyy and all that. So, for this one, A is going to be 1 and B is going to be minus 3 and C is 0. We can clearly see that there is no other derivative involved, therefore, rest of the derivatives are 0. So, for this B square minus 4AC is coming out to be 9 minus 0, so it is 9, so which is positive. Since all the coefficients are positive, both A and B are constants, therefore, the discriminant also will be constant in this case. So, it will be this partial differential equation will be of a particular nature throughout the region. So, the sign of the discriminant is positive, therefore, it is a hyperbolic partial differential equation, and since the coefficients are constant, therefore, it is hyperbolic everywhere. Now, let us find out this form also. So, for this A is 1, but here B is to be found out as minus 3 by 2 because we need to compare it with the second form. Let me show you the second form. So it is this only. So AUXX plus 2BUXY. So when we will write down this B, this 2 we need to consider. So whatever B is given here, the half of that will be taken. So from here, and C is 0 in this case. So if we find out AC minus B square, it comes out to be minus 9 by 4, which is negative, and therefore it is hyperbolic as per the conditions given. So we have seen that either method we can apply and the result is going to be same. So such a partial differential equation as the example 1 we have taken. So that partial differential equation is hyperbolic in nature. So we'll take a break here and we will resume rest of the part in the next part of the video.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Welcome to S. Chand Academy. So in the second part of the video, we will be discussing initial and boundary conditions. So in the first part of the video, we have learned how to classify a linear second order partial differential equation into hyperbolic, parabolic and elliptic type of partial differential equations. So we have learned two methods because there are two standard forms which are being used in different textbooks. So therefore, we have discussed both the forms there. So now we will be discussing that what do we mean by the initial conditions and boundary conditions. So first of all, we will discuss the boundary condition for the partial differential equation. So boundary condition expresses the behavior of the function at the boundary of the area of its definition. So suppose we are having a string here, which is of length L. So this end is at the length 0 and this end is at the length L. So if some conditions are given on these two boundaries, then they will be called as the boundary conditions. So there will be two type of boundary conditions. First type is called explicit boundary condition. And second type are called implicit boundary conditions. Implicit boundary conditions. So when we have implicit boundary conditions, then we need to solve them and then we will need to finally put them in the explicit form. So explicit form is more important for this. So there are three forms of explicit boundary conditions. The first form is called Dirichlet condition. Dirichlet conditions. The second type is called von Neumann conditions. Von Neumann conditions. And third type is called mixed, or they are called as Robbins conditions. So we will discuss them one by one. So first we will find out that when do we call a given condition as a Dirichlet boundary condition. So for Dirichlet conditions, now as we have discussed that it is one of the boundary conditions and boundary conditions are given at the end of the area of its definition. So suppose we take one example of this string of length L, then this end is at 0 and this end is at length L, so that the complete length of this string becomes L. if the value of this unknown function, so now here we are taking that the unknown function is u is the unknown function, unknown functions, and then x and t are the two independent variables, where t is the independent variables. Because if we are moving this string, then it is depending on two conditions. One is in this x direction in which this length is there. Another variable is time, because time at any point of time, suppose at any time is equal to 2 minutes or whatever is the unit of time for that particular question, it will be taken, suppose 2 minutes, we need to find out the wave in the string which has been generated at time t equals to 2 minutes. Then we need two independent variables to express this unknown function. So if the value of this unknown function at x equals to 0 and at any point of time, suppose this is given as some, say, function x, some function f1, and then the second condition is given at this end L. So one condition is given at this point and another condition is given at this point for the unknown function. And for the most convenient example is that, let us say that both are equal and both are equal to 0. So this is the most convenient example we can take for a Dirichlet type of boundary condition. So it is clear that we are given the value of the unknown function at both the ends, and that is why it is called Dirichlet type of boundary conditions. Now, the second type of condition is called von Neumann condition. So, second type of condition is called von Neumann condition. So since it is a boundary condition, therefore we are going to take the same example again. So this is the string of length L, and here the conditions are given at these two ends because they are the examples, they are the types of boundary conditions. But here, instead of the unknown function, its derivative is given at these 2 points. So let us say that del u over del x at 0 and t is given. And the simplest example is to take that they both are equals to 0. So let us say that this equals to 0. So if it is two ends are there for x, the value of x is this, x equal to 0 at the first end and x equal to L at the second end. Then if it is taken as the value of the derivative of u with respect to x only, it cannot be with respect to t, and with respect to x here at this end L is given, then it is called as the von Neumann type of boundary condition. Then we will see that when do we call it as mixed type condition or Robin's type of condition. Robin's conditions. So if it is a combination of the Dirichlet condition and the von Neumann condition, then it is called the mixed type of boundary condition. So it can be given as u0t plus del u by del x at 0t, and let us say this equals to some a, and then ult plus del u by del x at lt is equals to b. So if such type of conditions are given, they a or b need not to be constant, they may take some functions. So if this type of mixed conditions are given, that is, these are the Dirichlet condition and they are the von Neumann condition. So if it is a combination of both Dirichlet condition and von Neumann condition is given, it is called the mixed type of conditions or the Robin's conditions. So these if for a second order linear partial differential equation, two conditions are given, then the general solution must not have any unknown coefficients. So these three are called as the boundary conditions. Now one more thing is there, that it is not necessary that the first end should lie at the end x equal to 0. It is also possible that suppose this is ending, this is starting at C1 and this is starting at C2. So in that case, the condition will be given at C1 and C2. So it is not necessary that if one should be given at 0, x equal to 0, and another should be given at x equal to some other value. No, it should be strictly at the end points of the area in which the this unknown function has been defined. So we have to be very clear that if the length of the string is to be measured from say x equal to 2 to x equal to 4 for a particular example, then the conditions should be given at x equal to 2 and x equal to 3 instead of x equal to 0 and x equal to 3. So I hope it is clear to everyone. So then they are called as the boundary conditions. Then let us come to the initial conditions. Unlike boundary conditions, in boundary conditions, we are given that the string is there, and if we give some vibration in this string, then we need to observe this. We need to be given these conditions at both the ends of the string. If now, initial condition is, suppose we continue with the same example, that some string is given to us and which is starting from say x equal to 0 to x equal to L, and for this the independent variables are taken as x and t. They are the independent variables. And let us say that u x t is the unknown function. U x t is the unknown function. Now, when the condition is given in terms of the initial time, that is, if some condition is given as x u x 0 and it can be function of x, it can be constant, it can be anything. It cannot be function of t, of course. It can be function of x. So if such condition is given, this is called as the initial condition. When we use this word initial, we are referring to time in this case when we are taking this u x t as the vibration we have given in this string. Now, it is not necessary that the unknown function is given at t equals to 0, even its first order partial derivative can also be given, del u by del t at x 0. This can also be given. This will be also called as the initial condition only because they have been defined at time t equals to 0. So that is the difference between a boundary condition and an initial condition. The difference has to be very clear. There are three types of boundary condition, but there is only one type of initial condition, and when any condition is given at time t equals to 0, that is called initial condition. So we have learned the difference between boundary condition and initial condition by taking one example of a string. When the string has been tightened at both the ends at x equal to 0 and x equal to L, if some condition is given at x equal to 0 and x equal to L, they will be called as boundary condition. And if the value of the unknown function is given at these 2 points, then it will be called as Dirichlet condition. If its first order partial derivative is being given on this, they will be called as von Neumann condition. And if there will be a mixture of the unknown function and its first order partial derivative, they will be called as the Robbins condition or mixed type of boundary condition. In the similar example, if some condition is given in respect of time, that is the initial time, and it is not necessary, like boundary condition, it is not necessary that time should start from 0. Suppose in some case we would like to start from time is equal to 3 minutes. Then if this is the initial time from which we would like to observe the change, this is the initial time, then we need to be given this conditions like this. Del u by del x is equal to some function of x, and del u by del t x3 is function of. If such kind of conditions are given, they will also be called as initial conditions. So that's how we have learned the difference between the boundary conditions and the initial conditions. Whenever a linear partial differential equation of second order has, if two conditions are given, then the general solution cannot have any unknown coefficient.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.